how symmetry concepts apply to neutrino physics. And I'll use analogies to nucleon pairing, to the BCS model, and similar kind of pairing systems that we use in nuclear physics, so that it is familiar to a lot of us. The very, very first thing to notice is that if you look at the mass term in regular quantum field theory, if you write down the mass for a Dirac particle, which is what we call Dirac mass term for neutrinos, it actually is. Do we have a pointer?
Yes, it's one of those buttons. This way you can.
If you actually look at the Dirac mass term, actually the Hamiltonian of the Dirac mass term, it is a coupling between left-handed and right-handed components. But if you think a little bit, these are fermions. This really is something very much like the nucleon pair. As a matter of fact, this fact was noticed long time ago by Nambu, and it was the basis of his ideas about spontaneous symmetry breaking and so on. Of course, if the particles you are dealing with are charged particles, this is the only kind of mass term you can write that couples left and right-handed particles. But not much after Dirac had introduced this theory, Ettore Majorana came up with the idea that you can actually write down a mass term in the Lagrangian or Hamiltonian using only left-handed or right-handed particles using the concept of charge conjugation. So he did introduce these two different kinds of mass terms. This is the Majorana mass written in terms of the left-handed particles, and this is the Majorana mass written in terms of the right-handed particles. Now you may say, okay, that's good. Where is the symmetry? Well, those of us who worked on, those of you who worked on nuclear pairing problem for a lot of years, you know about the quasi-spin symmetry. And indeed, there is a quasi-spin symmetry here. If you define this quantity as d plus, d is for Dirac. If you define this quantity as d plus and its Hermitian conjugate as d minus, you know that the Dirac mass term is basically the sum of d plus and d minus. You can actually calculate, these are fermionic fields, calculate their commutator, and the operator you get d is this one, d0, and it's straightforward to show that d plus, d minus, and d0 form an SU2 algebra. Not surprising, but it is equivalent to the quasi-spin algebra for the nuclear pair. Well, it turns out you can do the same thing with the Majorana mass. If you write down this quantity, the left-handed Majorana, part of the left-handed Majorana mass, let me call that L plus, L means left, and it's L minus I will define as Hermitian conjugate of this quantity. Again, L plus and L minus together give me the Majorana mass Hamiltonian. And then you can actually calculate their commutators and get this operator as the L0, and you can again show that these three operators form an SU2 algebra. It's a different kind of quasi-spin algebra. You can do the same thing with the right-handed components, no problem. And you can also show that the right-handed components in the same way form an SU2 algebra. Well, it turns out these two algebras commute. So the most general Majorana mass term has an SU2 left cross SU2 right algebra that you can write down. Well, this is all very good. And you can also show that the sum of L0 and R0 gives you D0. So the other algebra that I call Dirac SU2 algebra is not independent of these two. It doesn't commute with these two. These two commute with each other, but the Dirac one doesn't. Well, this actually brings us to another Yale quasi-Gaussian. Well, it turns out you can ask, what is that algebra? What else is there? So what you do, you can calculate the commutator of d plus with L0, for example. You get these again. So these commutators give you what you had already. But these commutators give you two new operators, A plus and A minus. A plus and A minus. And A plus and A minus appear again. You can show, actually, that A plus, which is this quantity, it doesn't really matter exactly what it is, but it's again some pairing term. A minus is quantity. A plus and A minus also form an SU2 algebra if you define A0 to be the difference of R0 and L0. Remember, D0 was the sum, so L0, A0 is the difference. So altogether, you have these 10 operators. These 10 operators close under commutation relations. And those of us who had worked on pairing, we know that this is the SO5 algebra of the pairing. So those 10 operators form an SO5 algebra of the pairing. Well, that's very good. So we know what D's, L's, and R's do. They generate the masses, Dirac and Majorana masses. What about these A's? What do A's do? I'm going to call the SU2 algebra that one generate using A plus, A minus, and A0 to be the Pauli-Girsey algebra. And let's see why. Well, there is actually an old symmetry called Pauli-Girsey symmetry going back to 1957. And this is a particle, anti-particle asymmetry. Basically, it takes particles and transforms them into a combination of particles and antiparticles, they're charge conjugates. It's this transformation. This is the Pauli-Girsey transformation. Here A and B are constant, so that the absolute squares are 1, so that the commutation relations are satisfied. This was back in 1957, and I tried to find pictures of them from that time. As I mentioned, these 10 operators, D plus, D minus, L plus, L minus, L0, R plus, R minus, R0, A plus, A minus, form an algebra. That's the SO5 algebra. The most general neutrino mass Hamiltonian that is written here, that includes Dirac left-handed and right-handed Majorana masses, sits in the SO5 cross SU2 Pauli-Girsey, A plus, A minus, A2, times U1 coset. The U1 is generated by D0. And the rest, actually, rest is also quite interesting. The rest generates the Pauli-Girsey transformation. If you write down the most general element of the Pauli-Girsey group in terms of A plus, A minus, and A0, A minus, A plus, and this is the most general SU2 transformation, you can show that under this transformation, the spinor transforms in this exactly this way. And this is nothing but the Pauli-Girsey transformation with this A and this B. So you see this, the concept of pairing, if you think of it in terms of masses, not only give you more or less automatically Dirac and Majorana masses, but also the Pauli-Girsey transformation and resulting seesaw mechanism for generating small neutrino masses. This is all already in there and all in the symmetries of the problem. But I want to tell you a little bit more about other symmetries in neutrino physics. We heard about neutrino mixing. Neutrino mixing, of course, is a very modern topic. Many works have been done on it, and we now know that all three neutrinos mix. But just for simplicity, let me consider only two mass eigenstates just for illustration. We know that electroweak eigenstates are combination of mass eigenstates, where theta, or if you have three neutrinos, theta 1, 2, theta 2, 3, theta 1, 3, are mixed units. So why is this interesting? Because when an electron neutrino is emitted from a nucleus, it's in this particular state. That is the definition of the electron neutrino, that point. At time, of course, after some time t, it evolves separately because these two components have different masses and slightly different energies for the same momentum. So they evolve separately. As a result, after some time t, when you calculate, when you try to observe this, you find that some of it is the other flavor of neutrino, and that is the neutrino oscillations. And you can actually write down, I'm just going to show this to you, you can write down, this is the Schrödinger type equation, and write down the probability of survival. But of course, in vacuum, this is a dispersion relation between energy, momentum, and mass. In matter, things are a bit different. And this gives rise to what we call matter-enhanced neutrino oscillations. In matter, I mean, this thing comes from the Dirac equation. It comes from writing down the energy momentum connection in the Dirac equation. I don't really think I need this, do I? You can hear me just as well. I mean, I think it's just crazy. So this comes from the Dirac equation. Put particles in a medium, and of course they will interact with the medium. Imagine that you have neutrinos going through the sun or supernova, some astrophysical setting, or Earth even. Well, what kind of contribution you can have to the equation that describes the motion of the Dirac equation that describes the motion of neutrino? You can get either a scalar potential or a vector potential. The vector potential has to depend on other vectors, but that's the definition of the, I mean, when I say vector potential, I mean free vector. It has to depend on other vectors. Well, what other vectors can you imagine in the star, or in the sun, or in Earth? Well, I can imagine a current, matter flowing, a current. Or I can imagine polarization. That's a vector too, right? So, if I ignore the currents, if I say everything is charge neutral, charge neutrality is locally satisfied, and if I ignore polarization, external polarization, then there's really no free vector that characterizes the medium. So hence, there cannot be a free vector contribution to the potential. Well, scalar contribution can come from a number of things, but it has to be a scalar. And the most obvious scalar is the density of the background. So it doesn't take too much to think about that the scalar contribution will basically be proportional to the electron density of the background and a scalar, and the Fermi contribution. Now, of course, as I mentioned, neutrinos actually mix with 3 flavors, not with 2. And this is the most general mixing matrix. I can call them T23, T13, T12. Here, S13, for example, is the sign of theta 13, and this is a phase that violates the CP symmetry. You can actually write down that the MSW equation, basically, it is an evolution of this neutrino. It's basically this quantity here, mu e, mu and mu tau, are the potentials that electron mu or tau neutrinos will generate from interaction with the medium. That we can calculate also relatively easily. Well, it turns out the mu and tau, it turns out mu and tau neutrinos are such that mu and tau themselves, the charged leptons, are very heavy. In a lot of astrophysical settings where the neutrino energy is less than the muon or tau mass, you will not have charge current interactions of these neutrinos. So in most, they will only have neutral current interactions. As a result, these 2 neutrinos will not really matter. I mean, a lot of astrophysical phenomena will be blind to whether you are mu or tau type neutrino. So because of that, I can actually look at the combinations like this and reduce the equation in this form. Well, actually, at the tree level, neutral current contribution to all potentials are the same, but there are differences coming from loops. So that if you take out an overall phase to get rid of the trivial quantum phase, then this is the kind of potential that you get for the transportation. And again, the same thing. The dominant term is this one that was calculated by Wolfenstein. But as I mentioned, there are loop effects. Since the tau lepton is quite heavy, there are these additional terms that come in here that violate this mu-tau symmetry. Well, but I want to go one step beyond, and I want to think about astrophysical settings where we have a lot of neutrinos. And the motivation there is supernova, core-collapse supernova. A core-collapse supernova is a star where the progenitor star has more than 8 times the mass of the sun. It collapses, and it ends up with a very hot protoneutron star, and this protoneutron star cools. It can cool the best way by emitting neutrinos, because neutrinos do not interact with anything else. It actually emits the entire gravitational binding energy of the original star in terms of neutrinos. That's a lot of neutrinos. So a core collapse supernova is a factory that converts gravitational energy into neutrinos. In this particular case, you get about 10 to the 58 MeV, 10 to the 59 MeV energy released. And 99% of this energy is carried away by neutrinos. If you say every neutrino has 10 MeV energy, you are producing 10 to the 58 neutrinos. So the neutrino density far exceeds the nuclear matter density. That's actually an interesting point. Why is this interesting? This is interesting because we think that core collapse supernova are sites where our process nucleosynthesis takes place, and this is a possible site for the R process nucleosynthesis. And R process nucleosynthesis is also a rather universal thing. What is shown here is the elements of the R process produced elements shown created in two different sites. The red dots are those elements that are produced, that are observed in this distant star. It's an iron-poor star, hence it's an old star, not contaminated much. And the green line here is the solar system abundances scaled so that the overall scales are the same. I mean, overall scale depends on how much material you start with, so that's not an interesting quantity. What matters is the relative scales. And indeed, that shows you that there is a universal site for our process, nucleosynthesis. We just don't know where that is, but core collapse supernova is likely to be a site for this process. And also, our process abundances depend very strongly on electron fraction. Electron fraction is number of electrons divided by number of protons and neutrons. But if the medium is neutral, number of electrons and number of protons are the same. So electron fraction is a measure of the neutron to proton ratio. So electron fraction equal to 0, it means all neutrons. Electron fraction equal to 1 means all protons. So you can see, this is a calculation using the Fodor-Meyer. You can see that if the electron fraction, this is electron fraction 0.5, if the electron fraction is 0.5, same number of neutrons and protons, you really cannot produce most of the R process elements. You need rather low electron fraction or large neutron density in order to create conditions for R process nucleosynthesis. However, yields of R process nucleosynthesis are determined by the electron fraction, equivalent to by the neutron-proton ratio. However, interactions of the neutrinos and antineutrinos spinning out of the core, both with the nucleons and nuclei, determine this N/P ratio. So the conditions for R process nucleosynthesis in a core collapse supernova depend on the properties of neutrinos and depend on the properties of their interactions. The more importantly, as these neutrinos reach the R process region, they undergo matter-enhanced neutrino oscillations as well as coherently scatter of other neutrinos. Remember, 10 to the 58 neutrinos. Condensed matter physicists do many body physics of the materials. Materials have something like Avogadro number of electrons, 10 to the 23. In nuclei, we do many body physics for a density much less than that. So 10 to the 58 neutrinos in a short time, about 10 seconds, is a huge density of neutrinos around the protoneutron star. And because of that, neutrino-neutrino scattering, neutrino-neutrino interactions become extremely important. They actually become dominant. It is the only place where weak interactions actually drive a many-body system. I mean, in nuclear physics, strong interaction drives a many-body system. In condensed matter physics, it's the electromagnetic interactions. But this is the only case where the many-body system is driven by the weak interactions, and especially by the properties of neutrinos. Now, I want to tell you a few words about those properties. I don't know how much time I have left, but since I want to do everything in the context of many-body physics, I will, again, for simplicity, treat two flavors, and then add other flavors. That's not that difficult. And I'm going to write everything in terms of creation annihilation operators, so the similarity to many body physics is obvious. So what I have then, I have operators, A sub E and A sub X are the annihilation operators for an electron, neutrino, and other flavor with momentum P and spin S. You can use helicity if you wish. As we know, they mix under the neutrino mixing, and they give us matter states, and I will call matter states to be A1 and A2. Okay. Well, once you introduce, as you know, again, the same idea of quasi-spin. Once you introduce two kinds of fermions, you can always define a quasi-spin algebra. And indeed, there is a quasi-spin algebra here, and that's the flavor isospin. These three operators form the SU2 algebra. There are actually an infinite number of SU2 algebras, one for each neutrino momentum, and they all commute. That's not that complicated, and that's kind of straightforward. So you can actually write down vacuum oscillation term in terms of these operators, A1 dagger A1, A2 dagger A2. What I have done here again, I have taken a term which is proportional to identity, expanded energies in Taylor series, and kept the second term which deviates from the identity. So this is my vacuum oscillation term. Actually, if I define this vector, I mean, this is just a auxiliary vector, just a helpful definition, nothing else. This is not a magnetic field. A three vector, first component is sine 2 theta, second component 0, third component is minus 2 theta. This vacuum oscillation Hamiltonian is written, can be written simply in terms of linear combinations of the neutrino isospin flavor. You can also add the interaction with the electron background, the way we derive. That is proportional to J0. And then this is the most general Hamiltonian that describes the evolution of a neutrino through matter in the many-body language. All very good, but as I said, what really matters in supernova is the neutrino-neutrino interactions. So I have to put the two-body term here as well. As you know, one-body Hamiltonians are easy to deal with. We can solve them immediately. What really complicates, what brings the dynamics is the two-body. And two-body actually neutrino-neutrino interaction in this language is not that difficult to write down. It takes this particular form. It is a J dot J, this is neutrino flavor isospin, but for momentum P and momentum Q, but each such term is multiplied by 1 minus cosine theta, where this theta is not the mixing angle, but the angle between two neutrino momenta directions. It's this angle. The direction of the momentum P and the direction of momentum Q. This term follows from V minus A nature of the weak interactions. You can derive that. It's not that difficult. And of course, as a weak interaction, there's the Fermi constant. And since it's a two-body term, if you actually write down the Hamiltonian, remember in particle physics, people always write down the densities, not the total Hamiltonian. But if you actually write down the total Hamiltonian, then there is a 1 over V, which takes that into account. How much time do I have? Okay. I'll finish in less than 5 minutes.
Less than 5.
Okay, so then this is my total Hamiltonian. Many people worked on this, and you can see that this is a perfectly nice-looking Hamiltonian written in terms of symmetry generators and so on. And of course, you can actually write down a path integral for the evolution operator. But I won't go through that since this is well known to those of us who know such things well. But nevertheless, if you go through all that, you end up with an evolution equation like this. That really is not the basic thing I wanted to show you. So, and this comes from the mean field approximation. This connects to an RPA type approximation. I actually don't want to talk about that too much as well. And you can calculate corrections to it. Including anti-neutrinos is not all that difficult. It requires introduction of a second set of SU2 algebras. And you can include 3 flavors by doing everything in terms of SU3. I mean, that's Both are straightforward but tedious. The interesting quantity I want to show, the interesting thing I want to show you here, this is the Hamiltonian, and this is I would like to show you. In the approximation where this angle averages, which is a great approximation for the early universe, where everything is homogeneous and isotropic, probably not a great approximation to superquant. It takes this particular form. And if you define these quantities, you can write down the neutrino interaction Hamiltonian just like that. That really should look familiar to me. Well, there are invariants of this, that doesn't obvious invariance. That really looks like ordinary quasi-spin. And as a matter of fact, if I put them together, the neutrino-neutrino interaction Hamiltonian and the BCS Hamiltonian, where all pairing strengths are the same. Remember, I took 1 minus cosine theta came out. I said it averages to 0. That means all pairing strengths are the same. It is basically the same Hamiltonian. And you can actually, all the symmetries of the original BCS Hamiltonian actually are also true for the neutrino-neutrino interaction Hamiltonian. And that, I will not have time to talk about those, have very interesting implications for both the early universe and the supernova. And I will actually stop, but one thing I want to show you, you can also, again, this is symmetry. This is a very symmetric Hamiltonian. You expect to find constants of motion, and these are the constants of motion that you can find. Okay, I will, you can write down eigenvalues, eigenstates, everything that I'm not really going to bore with you. So if you are interested, we can discuss that. There's one interesting aspect. This interaction is actually observable. And that's what I should show you. This, because when you go to the mean field of this full many body Hamiltonian, I really didn't have time to talk about that. When you go to the mean field of this full many body Hamiltonian, you broke some symmetries. And you have to reinforce these symmetries by the Lagrange multipliers in your Hamiltonian. If you do that, these Lagrange multipliers actually would show up in the neutrino spectra, and it actually may be possible to observe them in the neutrino spectra that you observe on Earth. But since I don't have time to talk about those, I will skip that, but if you are interested, I'll be happy to talk. So let me start to examine the many neutrino gas, both from the exact many-body perspective, and also I didn't really have time to talk about our PA-type approach to it. And I showed some constants of motion, and well, why we should one actually study such systems and look at the symmetries when you say you can put them on the machine right away? Well, first of all, let me remind you, we're talking about 10 to the 58 neutrinos. It's very difficult to follow that numerically. And secondly, as Franco has taught us many times, one should also think, not just put things on the machine. And it's really, really important to understand the symmetries of the problem and how it may simplify and also solve the problem. In this case, I believe that these symmetries will go a long way towards the solution. Even if they don't give us the complete solution, I believe the symmetries I talked about, and I have some examples, I won't have time to talk about that, but also it's too technical. Some of the symmetries I talked about will simplify numerical calculations significantly. So Franco was right. It always pays to think before you put things on the machine. Thank you very much.